Hello, everyone, and welcome to today's webinar by LS Instruments. My name is Colin Bretz, Marketing and Sales Manager at LS Instruments, and it's a great pleasure for me to introduce our guest speaker of today, Professor Frank Sheffield from University of Fribourg. He will be telling us how to conduct error-free dynamic and static light scattering measurements using cross-correlation techniques. This webinar is interactive, and I encourage you to submit any question you may have using the chat that you can see on the lower right side of this webinar window. We will discuss your questions after the presentation, and a transcript of the Q&A session will be made available later on our website. Please also note that this event is being recorded, and you will also have the video available later on our website in the next few days. So, without further ado, let me now hand it over to Frank for the webinar.
Thank you very much, Colleen. I mean, it's also a real pleasure for me to be here and be able to present some of the things that we have developed already a while ago and that are now commercially available via LS Instruments. So my name is Frank Sheffield. I'm a professor at the Department of Physics and Fribourg Center for Nanomaterials at the University of Fribourg, and I'm also a member of the board of LS Instruments, just for full disclosure. So I'll start by introducing some basic principles of static and dynamic light scattering, and I'll highlight the challenges that people face when using these techniques, and then I'll explore the venue how to overcome these problems and provide solutions by 3D dynamic light scattering and most latest developed by us, modulated 3D technology. And at the end, I will briefly touch upon static light scattering, which can also benefit from these improvements or almost revolutions in light scattering. So let me first start by setting the stage by what kind of systems all of us are interested. So we are interested in polymers, macromolecules, small particles, clays, proteins, colloids. And these are all objects that are small so that they remain suspended by Brownian motion. So they're typically from a nanometer scale to a micrometer scale. And there's not all that much in terms of methods that you can use to characterize these systems. I mean, there are techniques like electron microscopy or atomic force microscopy that are very time consuming and expensive. And then you have equally neutron scattering, and therefore dynamic light scattering and also static light scattering have become really the tools of choice in many laboratories to study this type of systems, in particular particle sizes and interactions, and also sometimes shape of the particles if you think about depolarized light scattering. So I think most of us would agree that this is a very useful tool to study materials or objects in materials that are on these length scales. And this has consequences not only for fundamental research like in my laboratory, but also for many applications in daily life or in industry. So we all know that proteins, viruses, and antibodies are on the 100 nanometer or sub 100 nanometer length scales in size. There are microgels, there are other drug products or nanoparticles that are used for diagnostics. You have chemical materials that are used as polymers or nanoparticles, inks, and then you have all the way from the consumer products, food, dairy products, milk proteins, texture of food, and cosmetics. All these materials, a whole slew of materials are structured on the nano and mesoscale, and therefore we will wish to understand how these materials are built up and how we can characterize the building blocks of these materials. Very often these materials are also not super transparent, so we need to address the problem of strong scattering or multiple scattering. So the general idea of light scattering and dynamic light scattering is that we have a system like the one shown here on the bottom left. Let me try to put my laser pointer here. So here you have a container that contains some material like nanoparticles or polymers or proteins, and in a in a solution or dispersion. We have a laser beam that is incident on this sample in a container, and then we have a detector that records scattered light with very high precision. So this light scattering technique is very simple, much simpler than many other techniques where you first have to dry the sample in a controlled way and put it in an electron microscope, for example. It's non-destructive if you have the sample in solution or dispersion, and you get relatively quick and simple results, starting from particle sizes of a nanometer or a few nanometers all the way to several micrometers. You can also use light scattering to study structure and viscoelasticity. If you apply the so-called microreology approach, to this end you can use dynamic light scattering or diffusing wave spectroscopy, but for reasons of time I will not have time to go very deeply into this. I just want to mention that multiple scattering suppression, and in particular modulated 3D, is particularly useful if you want to apply dynamic light scattering for this purpose, because in these type of systems they are usually quite complex and there's a lot of background scattering. So here I would like to focus on the general principle and the methods that we use in dynamic light scattering from such system that is typically contained in a cylindrical cuvette that is 1 centimeter or so in diameter. Okay, the problem that everyone faces is that if you want to do such an experiment, you typically have to study single scattered or singly scattered light. So this means that we have an incident laser beam that goes in one direction. We have a scattered direction of photons where we put our detectors. A detector, this defines the scattering angle, and then the detector angle is equal to the scattering angle because there's only one angle. Now, if there is multiple scattering present, meaning that light is scattered at one angle and then is scattered again and again, or this would be triple scattering, or in double scattering, it's scattered once and then scattered again. There are already two scattering angles, and they have nothing to do with the angle between the detector and the incident direction of light. And therefore, in such a situation, you cannot back calculate, at least not easily, and in practice, it's impossible to back calculate what has actually contributed to your measured signal. And this contaminates your signal in an uncontrollable way and leads to erroneous results. So this has been known for a long time. This is also illustrated in my next slide when you go from single scattering to multiple scattering, just with a small video. So in single and multiple scattering, you have light scattering and multiple light scattering that you might be able to suppress, as I will explain in my next slides. And you can have extreme multiple scattering that you can then address with diffusing wave spectroscopy, which I will not talk about today. Now, if you have such a system like this switchable window that I recorded here with my cell phone, then you see you can go from transparent to completely opaque and turbid, from single scattering to multiple scattering in a controlled way, but usually you cannot control it electrically like in this fancy window, but your sample is what it is, and then you have to deal with the situation and you have to adapt your measurement technique in order to be able to measure your sample, or you have to modify your sample, which is not always advised. Okay, so the standard setup for dynamic and static light scattering looks like this, just to define the different elements that we are using here and in the other variants of cross-correlation. So we have now a bit more illustrative sketch of the experimental setup. We have the laser, we have the sample, we have the detected direction with a scattering angle theta, and then the light that is detected here is resolved with a photon counter that directly brings the signal or channels the signal to the so-called digital correlator. And then in a dynamic light scattering experiment, we measure fluctuations of intensity, or in actual live fluctuations of photon arrivals. We calculate from this the so-called intensity correlation function. So this is done by the photon correlator shown here as this box. And from this, then you can extract the information you like, for example, the particle size distribution. So this is a measure of the Brownian motion or the thermal motion of your objects inside the sample that you see here moving. So the faster those move, the faster this correlation function decays, and there are theoretical relationships, mathematical relationships between the motion of the objects and the correlation function that you measure that allow you to extract the information that you need if you have only single scattering. Now, if you have multiple scattering, the situation becomes more complicated. And this is shown here. Let's start from the right side. So here we have a highly multiple scattering white sample. If you put this in your dynamic light scattering apparatus, being a goniometer or a particle sizer, DLS particle sizer, then you will get a signal. You will measure something, but it can be completely wrong because your machine will not tell you that your measurement is wrong. So you have an undetectable systematic error in your measurement that you can only overcome if you do a dilution of your system or if you make the sample cell much smaller, thinner. If you have to do a dilution, then in principle you have to do a controlled dilution such that you find an asymptotic value, for example, of the particle size upon dilution that stabilizes and that tells you this is really the native particle size that I have or the native property I'm looking for. And it's really hard also to tell where does this multiple scattering contribution dominate, where does it end. So this is complicated and leading to systematic errors, and there are probably hundreds or thousands of papers in the literature where this has been ignored and false particle sizes, for example, have been reported. So this you don't know where you are with your system unless it's super dilute or super transparent. So you have to dilute your sample. You don't know exactly when you have enough diluted. If you dilute too much, you might have a lot of background from your solvent, depending on what kind of solvent you have, or if you have a biological system, you might have a lot of background scattering, and then you also have instrumental noise like dark count of the detector, and the whole thing is quite time consuming. So it's unreliable and time consuming, which warrants or asks really for a solution to this problem. And there has been a solution, and this solution has been proposed in its early stages already 40 years ago now, exactly. So there's a first paper in 1981 by Phillies that introduced the so-called cross-correlation multiple scattering suppression. At the time, this was done simply by putting laser and detector each at 90 degrees angle, so two lasers and two detectors. And this basically didn't allow the researchers to scan any angle, so this was fixed 90 degrees scattering with two lasers, so it was also reasonably complicated. Then in 1991, Klaus Schätzl proposed what we now call 3D cross-correlation dynamic light scattering, theoretically, but it was not implemented experimentally. And then in 1998, three groups, among those the group of Peter Schottenberger with Klaus Urban at the time, realized the first 3D light scattering apparatus together with two other groups in Germany. And then in my laboratory in 2010, we invented the modulated 3D that I will also present today, that was developed in collaboration with LS Instruments and licensed the technology and the patent by LS Instruments. And in this year, or developed some time ago, but patented this year, we have also the single beam modulated 3D light scattering, which works with a single beam and a modulator that not only shuts off and on the laser, but also redirects the laser in the appropriate optical pathway, which essentially allows very fast switching times and also allows a very compact design, much more compact than what we can realize with the traditional modulated 3D. So this depends on the range of application, whether you want a small instrument or you have a large instrument, what's more appropriate. Okay, so what is 3D light scattering? So the basic idea of 3D light scattering is that now we work with two beams instead of one beam. So we have two experiments running at the same time. So this is illustrated here in this sketch, graphical sketch. So we have a beam splitter half of the initial laser beam goes up, half of the initial laser beam is guided down. Both beams are focused in the same scattering volume, and on the other side we have a lens that is symmetric to the incident lens and guides the light to the two detectors. And the two detectors are vertical, such that the scattering angle for both is the same for the upper and the lower path. And then the analysis is essentially the same. Everything goes through a single photon counters and a correlator electronic device. This is a picture of the 3D light scattering apparatus that LS Instruments provides commercially. And here you see nicely, you don't see the lens, it's a bit outside, but you see nicely the crossing laser beams inside the sample that is a cylindrical cuvette here filled with a scattering sample that doesn't look all that turbid, but it's turbid enough to introduce error if you don't do the 3D light scattering. So more schematically here, you see again what happens. So we have the sample, we have the crossing beams that are inclined at a small but significant angle. And then you have on each detector you have some of the light that has been scattered only once, and you have some of the light that has been multiply scattered 2 or 3 more times. And the same thing you have on the other detector. And then if you do the cross correlation, then all the multiple scattering signal is filtered out or eliminated, and it only contributes to the background. So in the end, you only measure the single scattering correlation function or signal. So this is the important principle of 3D cross-correlation light scattering, where multiple scattering is only a random component in the signal that is detected by the electronics or by the instrument. Okay, so this 3D correlation acts like a filter to remove any multiple scattering contribution. The next slide, I have an in-depth view of this principle that is also for the experts. So I want to spend a little bit of time on the basics of this light scattering principle without going too much into the mathematical details. So here I've sketched again by hand the traditional standard DLS and SLS geometry. So we have the scattering plane here that you see here. We have the incident wave vector K1 in. We have the scattered wave vector K1 out. We have the scattering angle. The scattering vector is defined as 2 times the modulus of K times the sine of the half of the scattering angle. You can look at the top view. Then you see again the scattering vector here. And the modulus is the same for the incoming and the scattered wave. Now you incline the plane a little bit by half an angle theta, delta, such that you introduce the 3D geometry in the experiment. And this is shown on the right-hand side. So now we have an upper K2 in, we have a lower K1 in, we have a K1 out that is detected, and we have a K2 out that is detected. And now we have 4 possible combinations of scattering vectors between these in and out wave vectors. And as I said, I don't want to go too deep into the theory, but I just want to show this here. So we have these 4 combinations. Only one of these 4 combinations has the same Q1 and Q2. So the difference between out and in is the same. And this selects and filters the single scattering signal. All others create only random signals. So we have 3 components that create random signals. This suppresses the signal by a factor 1/4 without changing the quality of the signal, but it reduces signal to noise. And then if you get additional multiple scattering, it further reduces the signal to noise without altering the quality of the information, because multiple scattering is not affecting the signal shape, for example, the correlation function. And the suppression of multiple scattering can be shown is better than a factor 1,000, and it's set by how much you incline these 2 planes. And in practice, it has been shown over and over again that the signal to noise is the limiting factor and not the multiple scattering suppression. because the dynamic range you have, 1,000, is already a lot, and you will not be able to explore the problem of this being not being good enough to suppress multiple scattering. So for all practical purposes, multiple scattering suppression is perfect, but you have still to deal with limited signal to noise in your experiment. Next, I would like to comment on the difference between cross-correlation, what we call true cross-correlation, which would be 3D cross-correlation, and pseudo cross-correlation, because other instruments or common instruments also propose or allow for cross-correlation, but this is simply meant to eliminate detector noise. This has nothing to do with multiple scattering suppression. The idea is that in a classical DLS experiment, you would take the light that you detect with your fiber receiver, and instead of guiding it only to one photon counter, you would split it with a splitted fiber and guide it to two, and then you cross-correlate the signal with itself. So you're essentially just taking, instead of correlating the signal with itself on one detector, you do it on two. This gives you exactly the same signal, but it removes correlated noise between the detectors, because you have two different detectors, so they don't know of each other. So you can suppress detector noise, which is called after pulsing, and this is important to study fast processes, but has nothing to do with multiple scattering suppression. Now, in true cross-correlation, we have two detectors and two fibers and fiber receivers, and they are cross-correlated. So this true cross-correlation both suppresses multiple scattering and eliminates electronic noise or electronic after pulsing. So this is important. The first one only suppresses the detector noise, has nothing to do with multiple scattering. The second realization that we propose, suppresses both multiple scattering and eliminates detector noise. Okay, so what about this signal to noise? What is the signal? What is the noise? So in any type of dynamic light scattering experiment, you measure this type of correlation function. So if you plot it in the way I plot it here, so this is the intensity correlation function -1. So this is a function that starts at 1 and drops to 0. So you have two limits. You have the 0 time limit, which gives you the amplitude here, or the intercept, we call it often. And then you have the baseline here zoomed in with this magnifying glass. So the baseline quality, so how well you can measure this baseline, depends a bit on how long you measure and how stable your system is. But here, for the sake of the argument, I give an order of magnitude 10 to the -3. So if you start at 1 and you go to 10 to the -3, then you have signal to noise about 1,000. However, if you do the true cross-correlation, the 3D cross-correlation, your signal is suppressed by a factor of 4 due to this combination of wave vectors that I just explained in this in-depth view of the cross-correlation technique. So this is unavoidable in the classical implementation of 3D cross-correlation. So the signal to noise is reduced by a factor of 4. It's not much, but I mean, if you give up on a factor of 4 and you only have a factor of 100 to 1,000, then this can be disadvantages, and it's better to overcome it. And if you could overcome this, then you get a much better signal to noise, and you could measure much faster the same data. So how do we do that? For this purpose, or for this to this end, we introduced modulated 3D light scattering in 2010, published in this paper below. So now, instead of having continuously the two laser beams illuminating the sample and the two detectors on, we time gate the experiment. So at any given time, there's only one laser beam on and one detector receiving. And this way we can select the Q1, Q2 that I showed you before. So we only measure the one single scattering, identical scattering experiment each time that fits to each other. And we don't measure these three other combinations that don't contribute to our signal, that only contribute to the noise. In very lay terms, simple terms. And by this gating, and this can be done, and this has been maybe not easily possible 40 years ago, but with modern electronics, fast modulators, and fast detectors, this can be implemented at a reasonable cost. So this has the advantage that we can have a 4 times higher signal and measure faster, or depending on what is more important for you, you can either measure more turbid samples, therefore this raises the highest concentration measurable, or you can measure more samples in a certain given time. There's one limitation or a cutoff due to the speed of the modulators, and this is currently 0.8 microseconds, which is very fast, which means that these modulators switch back and forth faster than 1 megahertz, 1 million times per second. And this is not really a problem because large objects lead to time relaxations on the millisecond scale, and very small objects like proteins would decay a bit faster. It's still within the window of modulated 3D, but if needed, you could also switch back to 3D cross-correlation, which can go down to 10 nanoseconds in time resolution, or you could, if the sample is very transparent, also and dilute, you could also go back to standard DLS, all of which is implemented in typical experimental designs of this system. So to give you some examples of the performance, I show you here a comparison between standard dynamic light scattering, modulated 3D, and 3D cross correlation. So this, what is important here, that these three curve, if they are in single scattering, you can rescale them on one curve simply by changing the amplitude, the intercept. But as you increase the turbidity, the standard DLS will give you erroneous results, whereas modulated 3D and 3D cross correlation will give you the same correct results, the true result, but with different signal to noise ratio. And this is shown on the right. So we start on the right-hand side with a sample that is very dilute and has a very high transmission. And then we increase the concentration of the particles. These are 100 nanometer polystyrene particles, if I'm not mistaken. And then you see the standard DLS particle size that you measure decreases by a factor of 3, will be wrong by a factor of 3, whereas the 3D cross correlation and the modulated 3D cross correlation remain constant at about 45 nanometer radius, but the noise, so the error bar of the standard 3D cross correlation will become very high if you have very low transmission, meaning that the sample is very, very multiple scattering, very turbid. Here you see that we have like 0.2 transmission of the direct laser beam through the sample. We can still measure with a 10% precision the particle size. So this really shows the power of this modulated 3D technology also, and principle also for particle sizing. Okay, just to summarize, so we have this 3D filter optimized by using the modulation to filter out multiple scattering, which gives us an error-free signal that is only single scattered light. And this has been developed, initially proposed by Schätzl, implemented by Peter Schottenberger and others, and then optimized by us in the frame of this collaboration with the University of Fribourg and LS Instrument, funded by the Swiss Commission for Technology and Innovation around 10 years ago, and now already commercially available for a couple of years. Here is another example for increasing the concentration of polystyrene spheres, where you again see the differences in a more recent example of particle sizes measured. So this is a bit larger particle size, and how the particle size that you would measure with now compared to a standard DLS particle sizer. Before it was compared to standard DLS using the LS Instrument goniometer. Now we also compare it to other companies' standard DLS particle sizer, and you see that in a standard DLS particle sizer you would just measure completely wrong results if you have a sample that has a lot of multiple scattering contributing to your signal. And here you see the relative error as a function of the volume fraction of the polystyrene spheres in this case. And there's no warning given to you by the instrument, by the standard DLS particle sizer instrument, because the particle sizer doesn't know what is your concentration. The particle sizer just measures light that is scattered, and the system doesn't know, the instrument doesn't know where the light comes from. And modulated 3D or 3D cross correlation are automatically only detecting single scattered light, and they cannot be fooled by a 2 turbid sample. Okay, I have a few more slides, just more different variants and applications. So one is that, as I mentioned before, if you drive this a little bit farther and you want to work with a single modulator, and this has been implemented by LS Instruments. I've not been involved in this, just to complete the story. You can use the modulator not only to turn the light on and off, but also change direction. This is a light modulator that deviates, an acousto-optic light modulator that deviates the incident laser beam. And if you arrange the optical fibers in a smart way, then you can channel or direct the laser through one or the other, and then you can operate the whole experiment with one modulator and also one laser, and therefore you double the laser power, you increase the speed, and I have a problem here. You increase the speed, you have less elements, and you have simply more compact design of the instrument, and this has been implemented in the nanolab variant of the 3D modulated technology, where space is definitely an issue, whereas for the goniometer system, the 3D modulated 3D goniometer system, space is not as much of an issue as for the compact particle sizer instrument nanolab 3D. Okay, last but not least, I'd like to say 2 or 3 words about static light scattering. So all of what I said can also be applied to static light scattering. And here we use the following principle. So in static light scattering, what you typically do is you scan the angular distribution of intensity. And from this, you get something like the shape form factor of the suspended particles or objects, polymers or particles. And therefore you can get the size and size distribution, and you take the intensity average. So in a classical experiment, you would not look at fluctuations like in dynamic light scattering, but simply at the average intensity as a function of angle. Now in 3D light scattering or modulated 3D, now you can correct any signal that you measure by the relative contribution of multiple scattering. And this looks a bit complicated, but in practice, it's actually not too difficult. I have to make space here. Apologies for 1 second of interruption. So now, so what happens if you increase the turbidity of your sample, meaning that the total transmission through your sample would decrease? This is shown here on the right-hand side, again, as before. So 100% transmission means that your sample is almost transparent. And in this case, you see the maximum signal, maximum intercept called beta, which for standard DLS is in blue, is almost 1. For Mod 3D, it's also almost 1. There's a small reduction due to geometrical reasons to about 0.85 or something like that. And then you have the classical 3D cross correlation, where you have a signal that is about 0.2, reduced by a factor of 4 compared to the modulated 3D. Now you increase the turbidity, then you get a decrease of the intercept, because now you have a mix of single scattering and multiple scattering. The single scattering doesn't contribute to beta. The multiple scattering doesn't contribute to beta, but the single scattering does. And the more multiple scattering you have, the lower the signal, the lower the intercept. But this you measure, so you measure this value. Now you can back calculate how much of the light that you measured is single scattering and how much is multiple scattering. And this is there's a simple formula that you can use by averaging over both detection channels. So the single scattering intensity is the square root of the product of the single scattering intensities of each channel. That's trivial. And this you get by multiplying each intensity or count rate that you measured on each detector, 1 and 2, and the ratio of these measured intercept to the perfect intercept or amplitude. I give you an example. It doesn't look so dry. It's relatively easy. You know the maximum intercept being, let's say, 0.05. This is calibrated in the instrument. You measure an intercept that is 0.1. You have two count rates. All of this is given by the instrument. Let's say 150 kilohertz and 130 kilohertz. Then you simply multiply 150 times 130 times, okay, now I made a mistake, I apologize. This should be 0.1 divided by 0.85. Take the square root, and then you get the real single scattered count rate that you measure at this particular angle or scattering vector in your experiment. So you can back calculate the single scattered intensity at any angle. And here's an example that we also measured at the time, but there are many more. Here you see a particle form factor, so an angular scan in degrees now of the scattered intensity or count rate. In standard SLS, meaning no multiple scattering correction, you see this is what you measure, this is what you expect from scattering theory. Me theory is completely off, completely smeared out due to the multiple scattering. You correct the single scattering contribution by the using the formula that I showed you on the previous slide. Now the data follows the expected curve, but with some noise where the signal to noise is simply not good enough. Now you do the same thing with the modulated 3D, then you get even better agreement, even close to the minimum of this scattering curve or form factor. In both cases, standard static light scattering is completely off, whereas 3D and modulated 3D light scattering can provide both dynamic light scattering information accurately and static light scattering information by using this back calculation formalism. Okay, I would like to summarize. I think I'm good in time. What I wanted to convey here to you, that light scattering is a really powerful method to characterize systems like particle suspensions, protein and polymer solutions that many of you are interested to study. It's often limited by multiple scattering, in particular if you have real-world systems that you cannot design in order to be optimal for the experiment, but that you have to take as they are. And for this type of system in general, it's very practical and convenient and useful and powerful to filter out multiple scattering through the cross-correlation principle, and modulated 3D gives you the best signal to noise and the fastest measurement, and both of and this technique can be beneficial both for dynamic light scattering and static light scattering. And with this, I'd like to thank everyone who attended for coming and for your attention. I've compiled here a list of the technical reading that I mentioned in my webinar. And if you would like to learn more about applications, then you should check with Colleen and on the website of LS Instruments what applications can be addressed. Many can, but she can give you more information, or you can read the literature on these topics. Thank you for your attention, and I'll hand over to Colleen.
Thank you very much, Frank, for the excellent presentation. And in this last slide, I would like to provide a few more resources for people who are curious, especially in the instrumental implementation of the modulated 3D technology. So this technology is embedded in our instrument, which you can see on the right side of the slide. We have the NanoLab 3D, which is a compact DLS particle sizer that can measure, of course, particle size for dispersity, but also viscosity in small sample volumes. Then we also offer the LS spectrometer, which is a DLS and SLS system that can characterize particle size, particle shape, molecular weight, and many other parameters. And if you would like to reach out to us or simply keep informed about future webinars, please visit our website, write to us, or follow us on social media. And again, I would like to thank everyone again for joining us today, and thank you especially to you, Frank, for the excellent presentation. We really appreciate your participation.
Thank you for all coming, and have a nice afternoon or morning wherever you are.